Hey everyone, so these are the solutions to Worksheet 2.4. Here we're going to be talking about solving inequalities that involve absolute value functions as well as quadratics. The techniques are slightly different for the two, so make sure you're paying attention to the different methods that we use here. So we're going to start off with some absolute value inequalities. First, we've got the absolute value of 3x minus 5 is less than or equal to 4. So what we're doing is we're looking for the values of x that maintain this inequality here. Now with absolute values, we have to remember that since we're taking the absolute value of, in this case, 3x minus 5, we need to, as in within the equations, we need to account for the possibility that that expression could have been a positive or a negative version of what's inside the absolute value bars. So inevitably what we have to do is we have to set up two different, in this case, inequalities. So let's start with the positive version. So the first one that we're going to do is we're going to set up what if we had just 3x minus 5 needs to be less than or equal to positive 4, and find the values of x to satisfy that inequality. And then along with that, we're also going to consider, well, what if that 3x minus 5 had actually been a negative version? And then we say, well, one in that is less than or equal to positive 4. Okay, so we're going to need to solve both of these. Let's start off with our first one. So pretty straightforward. We just solve this for x. I'm going to go ahead and add 5 to both sides, which will give me 3x is less than or equal to 9. And then go ahead and divide both sides by positive 3. So that's going to give me x is less than or equal to 3. So those are the values of x that would satisfy this first inequality. Now we need to check the values of x for this second possible scenario for our absolute value inequality. Now the first thing that I'm going to do here is I'm going to go ahead and take care of that negative by multiplying both sides right off the bat by -1. So I'm going to multiply by -1 on both sides. And in doing this, since we're multiplying, and this works for division as well, but for both of these, if we multiply or divide an inequality by a negative value, we need to change the inequality sign. So I'll just put a note here to be sure to flip the inequality. So the inequality sign. Okay, so if we do that, if I multiply both sides by -1, that's just going to make this 3x minus 5. The 4 is going to become -4, and then we're going to flip the inequality sign. Now, some of you might be used to just jumping straight to this step, and that's fine, but I think it's good to see why we need to do that in this case. So now we'll just go ahead and, as with the other one, we're going to solve this for x. So I'm going to go ahead and add 5 to both sides. So that's going to give me 3x is greater than or equal to positive 1. Divide both sides by 3. And that's going to give me x is greater than or equal to positive 1/3. So now what we have to do is we've got to figure out a way to come up with an interval that satisfies these two conditions for x. Now, I feel that a really useful tool in doing this is to go to interval notation, is to set up a real number line. And you'll see that the authors in the text use this a lot as well. So I'm going to go ahead and just plop up a number line that goes from -infinity to positive infinity. And I'm going to drop down these two key points here. So we've got 1/3, and we've also got positive 3. So let's go ahead and just sort of plot these two conditions. So this first one says that x is less than or equal to positive 3. So the way that we would put that on the real number line is we would say, well, x could be equal to positive 3, or it could be less than. So that's this stretch of the real number line. Now the other condition that we have here is that x needs to be greater than or equal to positive 1/3. So if we were to plot that on, we'd say, well, here's equal to positive 1/3 right there, and then this would be the interval of greater than. So what we have here is, if we were to put them on top of each other, it looks like it's covering the entire real number line. But in these cases where we have overlapping intervals, what we're going to look for is the the intersection of these two. So in this particular case, the overlap would be our solution interval, which is going to be from 1/3 to +3. And since we want to include both of those, we're going to use brackets for this. So this would actually be our solution right here, the interval from +1/3 to +3, inclusive on both those endpoints. So let's go ahead and try this again with another one. So it's going to be the same sort of setup. I'm going to go ahead and I'm going to break this up into two different inequalities that we will then solve for. So we've got 7x plus 2 is strictly greater than +10. And we've also got negative quantity 7x plus 2 is strictly greater than 10. So those are the two cases that the absolute value implies here. So if we go to solve this first one, we subtract 2. We're going to get 7x is strictly greater than 8, and divide both sides by 7, and that's going to give us x is greater than 8/7. Okay, so there's one. For this next one, again, I'm going to go ahead and multiply both sides by -1, and that's going to give me 7x plus 2 is strictly less than, so we flip the sign, the inequality sign, and then we also change the +10 to a -10. Now we go ahead and we solve for x. By the way, just as an aside, if you had wanted to distribute this negative through, you'd still end up with the same solution. But just thought I'd mention that. So we'll go ahead, we'll subtract 2, which gives us 7x is strictly less than -12. Divide both sides by +7, and we get x is strictly less than -12/7. Okay, so these are the two conditions that we want to account for in our solution interval. So again, I'm going to go ahead and I'm going to sketch out a real number line and plot these two individual intervals. I know this might seem like a little extra work, but once you do a few of these, this becomes a pretty easy task. So we've got -12/7 over here, and then we've got +8/7 over here. So let's go ahead and drop down these points in the real number line. So x needs to be strictly greater than 8/7. So strictly greater means we're not going to include 8/7, but we are going to include all of these points greater than. And then for x is strictly less than -12/7, again, strictly less than, we don't include it, specifically that point, but we're going to go ahead and take on all these points less than. Okay, so we have two non-overlapping intervals. So in this case, when they're not overlapping, we're going to our solution is going to actually be the union of these two individual intervals. So we're going to go ahead and say that this solution will be from -∞, and we always use parentheses with infinity because infinity is not a number, so we can't include it. And then we go to -12/7, and that will be a parentheses also because we can't include it. And this other interval will be from 8/7, non-inclusive, to +∞. And since we want the union of these two, we just put this big old U in between, and that stands for the union. So we could pick a point in either of these two intervals, and it would satisfy this original equation, or inequality, excuse me, that we had up there. So this would be our solution to number 2. Okay, so for number 3, we are now going to look at solving a quadratic inequality. Now, the technique that we're going to go over here to solve these quadratic inequalities is something that you can apply to any inequality that you may run across, and it's actually a preferred method once we get beyond the more basic inequalities that involve things like linear functions and absolute value linear functions like we just did. So this is something that that you'll use a lot in pre-calculus, and you'll also use quite a bit when you get into calculus. So this is the basic idea of what we're going to be doing here. So our first step in solving these, just a little outline, is let's go ahead and get 0. I'm just going to strike that through. So get 0 on one side of the inequality and the function on the other. in this case it's a quadratic function. So essentially you want to isolate that function. Okay, so that's the first thing that we're going to do. Now, once we've isolated the function part of our inequality, we're going to want to go ahead and find the zeros of our function. So find the zeros of the function. And then third, and there's a little bit more to it than just saying this, but we're going to make a sign diagram. And from this sign diagram, we're going to be able to evaluate our inequality by testing points. So we make it a sign diagram and test points. So you've probably done this in class, but we'll go ahead and we'll outline how we do that. All right, so we're going to go ahead and use this method to solve this first inequality here. So let's try step one. So we want to have 0 on one side and the function on the other. Well, this is great. We've already got that. So we've already got x squared plus 2x minus 3 is greater than or equal to 0. It's also kind of, I think it might be a good exercise here to really think about what this is asking us. So we've got this function, x squared plus 2x minus 3. And what we're trying to find out here is, when is this function? So to translate this notation, when is the function, in this case x squared plus 2x minus 3, now it's asking for greater than or equal to 0. So when is this function positive or equal to 0? So this is really the question that we should be asking ourselves as we go through this. When is this function that we've isolated now going to be, in this case, positive or equal to 0? So we're going to answer the equal to 0 question in this second step. So we're going to go ahead and we're going to take the function x squared plus 2x minus 3. We're going to find the zeros by setting equal to 0 and solving. We could try factoring. We could use the quadratic formula. In this particular case, it is going to factor rather nicely. So we've got x plus 3, x minus 1 equals 0. So the fact that the product of these two factors is equal to 0 tells us that one of these factors has to be equal to 0. So zero product property tells us that. And now we can solve both of these for x. So the conclusion that we can draw from this is that x has to be equal to -3 or 1. So these are our zeros. These are going to be the points that we now use in step 3 to create this sign diagram, test points, and evaluate our inequality. So kind of like we did in the last one, I'm going to go ahead and start by drawing a real number line. Maybe we'll try and draw a straighter line than that. Okay, so we got our number line, which is going from -infinity all the way to +infinity, and we're going to drop down our 2 points. So we'll put -3 right here, and then we'll put, actually, I'm going to go ahead and put it down here. So put the -3 there. We'll put the +1 down here, and it's not necessary that you do this for now, but later on when we get into other types of functions, it might be helpful to make note that what's going on at each of these points, these are our zeros, in case we forgot. So I'm just going to mark that with a little sign that tells me these are the points where my function is actually equal to 0. These are the zeros of the function. Okay, so we've got this set up. Now what we're going to do is we're going to go inside each of these 3 intervals. So we've broken the real number line up into 3 different parts. And we're going to pick a point from each of these to test into our function. And what that's going to tell us is, well, if we can show that, say, this interval right here, by picking one point, the function comes back positive, then that tells us that the function is going to be positive over this entire interval because of what we get from that one test point. And we do that 3 times. So it's probably a little bit clearer once we do this. So I'm going to pick a point. You could really do anything, but I like to pick points that are maybe a little bit easier to calculate. In this case, I'm going to pick -10 as my test point from this first one. If you can get 0, that's always a really easy one. And then I'm going to use +10 over here. Okay, so let's go ahead and do our testing. So we're going to do our test points. And remember that our function is that x squared plus 2x minus 3. That's what we're going to be plugging these values into. So we're asked to evaluate f of negative 10. We plug negative 10 into our original function. So that's going to be negative 10 quantity squared plus 2 times negative 10 minus 3. And we can go ahead and we can calculate this out. So this is going to give us 100 minus 20 minus 3, which gives us what, 77. Now that's all well and good, but really all we care about is whether or not this number is a positive number or a negative number. And in this case, it's a positive number. So what we're going to do is we're going to take that information and then put it back over here on our sign diagram. So that interval, on that entire interval from negative infinity to negative 3, our function is positive. We're going to repeat this process for each of the test points. So next we'll do f of 0. This will be an easy one. So we've got 0 squared plus 2 times 0 minus 3. So that's just going to leave us with minus 3. And minus 3 is clearly a negative number. So on this interval that included that test point 0, our function is going to be negative on that interval. And then the last one we'll do is we'll do the positive 10. And if we plug 10 squared plus 2 times positive 10 minus 3, we'll get 100 plus 20 minus 3, which is going to give us 117. And again, this is a positive number, so we're going to put a plus on our sign diagram for that interval. Okay, so now we've got to get to the part of actually evaluating this. So we were asked, if you remember up here, when is this function positive or equal to 0? That's our interpretation of the original question. When is that function greater than or equal to 0? Well, we can pick out a few things already. It's equal to 0 at the zeros. So I'm going to go ahead and fill those in first. So those are 2 points that I want on my interval. And then I also want to know when it's positive. And we can see that it's positive on this interval right here, and then on this interval right here. And then in between, the function is negative. We can tell that from our test points. So now we've got our solution, and we can just go ahead and put it together. So we've got it from negative infinity to negative 3, which we will include because it's equal to 0 there. And then we've got the interval from positive 1 to positive infinity, and again we're looking at the union of these two intervals, so we put the union symbol in between them, and then that's our solution for that one. So that's how we use sign diagrams to help us evaluate inequalities. Okay, so let's do one more like that. So here we've got x is strictly greater than x squared. So we're still going to go and follow those 3 steps that we outlined in number 3. So let's start with step 1. So step 1, we want to isolate the function and get 0 on the other side. So I'm just going to go ahead and subtract that x from both sides. That's going to give me 0 greater than, and then x squared minus x. If you had moved the x squared to the other side, it would have been fine. You're still going to end up with the same solution as long as you're careful with your signs and everything. So it's totally up to you. And again, we're looking at this, and this is essentially asking us when, or for what x values, when is the function x squared minus x strictly less than 0. That's a 0 there. Essentially, when is it negative, right? That's what we're going to be looking for. Okay, so step 2, we got to find the zeros of our function. So we're going to take x squared minus x. We're going to set that equal to 0 and then solve. Again, quadratic, you could use a quadratic formula. Probably the easiest thing to do here is factor out a common factor of x, which is going to leave us with x minus 1 times x is equal to 0. So that tells us that either x is equal to 0 or x minus 1 is equal to 0. So the two zeros of our function that we get are x equals 0 and positive 1. So those are the 2 points we're now going to use in step 3 to create our sign chart or our sign diagram. So we've got our real number, squiggle. I don't know if I can really call that a line in good faith. So now we're going to go ahead and we're going to drop our points. So 0 and positive 1. And again, I just like to do this to keep things straight. I know that that's a 0 of my function. This is another place where my function is equal to 0 to keep track. And now we'll go ahead and we'll test points. So what points do we want to pick? Again, you can really have free reign to pick whatever. I'd say just pick things that are easier to use. I'm going to go ahead again and pick -10 because 10 is an easy one to work with. I'm going to pick a half from this middle interval, and then positive 10 from this other one. So let's go ahead and we'll test our points. So I'm going to take f of -10. Now, we really don't need to find the exact value here because the only thing we really care about is whether or not it's positive or negative. So if it's clear to us that we're dealing with a positive or a negative number without having to calculate the actual value in this process, that's okay. And we'll see that if we picked -10, we'd have -10 squared minus 10. That's clearly going to be a positive number, because we're going to have positive 100, positive 10. So we can just kind of go through here. If we picked f of 1/2, this is probably going to require us to do a calculation just to be sure, but we'd take the positive 1/2, we'd square it, and then we would subtract 1/2. 1/2 squared is a fourth minus a half. So we're taking a fourth, we're subtracting a half, which is a number larger than that. So what we're going to end up with is a negative number here. And then lastly, we've got f of positive 10. So we've got 10 squared, which is going to be 100, minus 10. And again, that's going to give us a positive number. Okay, so let's go ahead and take this information and plop it on our sign chart. So the interval with -10 is positive, the interval with the 1/2 is negative, and the interval with the positive 10 is positive. So now let's go ahead and answer the question. When is x squared minus x, this function we just tested, strictly less than 0? So strictly less than means we're not going to include the zeros. So rather than filling in solid dots on both of these zeros, I'm going to put open dots to signify we're not using them. And then I'm going to look for the interval that my function is negative over, and that's this middle one right here, because the other two are positive. So my solution interval is going to be from 0 to 1 and non-inclusive. So again, what we've concluded is that we could pick any number between 0 and 1, not including 0 and 1. We could put it back into this original inequality, and we would have a true statement, and that would hold true for that inequality. Okay, so that does it for this. There's going to be plenty more work with inequalities as we start learning about more functions, but until then, I'll see you guys in the next video.